Okay, Chapter 6, we're going to be covering what is called a discrete probability distributions. There's going to be a couple calculations that are going to be a little bit new. One's going to be for what's called the expected value and the variance, which are going to be slightly different than what you've seen in the previous chapters. But I think if you just follow the examples and the symbols, it's actually not too bad. Okay, so again, here we go. So Chapter 6. So first of all, we talk about what's called a probability distribution, which is basically you list all of your outcomes and then you list also the probabilities that are associated with each outcome. And let's kind of make a note here. This is kind of like your relative frequency distribution that we've already looked at in the previous chapters, except in this chapter they just call it a probability distribution, but you've actually already done this, and you'll see that coming up in a moment. A couple characteristics is that typically you're going to find in these probability distributions that it's the same rules as before. The range of probabilities is always 0, always up to 1. The outcomes for each outcome are said to be mutually exclusive. The list is exhaustive, but again, the idea is that the sum of your probabilities should always equal 1. So in this example, you're listing a probability distribution if you tossed a coin 3 times. And so, for example, if you tossed it the first time, there's 2 outcomes. You tossed it the second time, there's 2 outcomes. And you tossed it the third time, there's another 2 outcomes. And following your basic rule of multiple step outcomes, to get the total number of outcomes is 2 times 2 times 2, which is 8. And they listed all of these outcomes right here. Now, over here it represents what we're looking for, which is how many times did we land on the heads. And so, for example, on all these scenarios, we can see that there were 0 times, in other words, that we got all tails. That's a possibility. And looks like there's at least 1, 2, 3 times you got heads once. Looks like 1, 2, 3, 2 times you got heads twice. And then there was only 1 time that you got heads 1 time again. And so, again, remember the basic 1 divided by n probability concept, or 1/8, is a possibility for each one of these outcomes. And so if you follow this distribution, x, which is going to represent the number of heads could have represented either 0, 1, 2, or 3. And then in order to assign a probability to each one of these outcomes for the number of heads, we're going to follow this 1/8, and we simply would go to this column and start counting. So for example, 0 times, that happened once, so that would be 1 divided by 8. 1 time happened 1, 2, 3 times, so that would be 3 divided by 8. 2 times happened 1, 2, 3 times, that's going to be 3/8. And it landed on the heads 3 times, that only happened 1. That's one possibility. That would be 1/8. So again, in the next slide, I'm going to show you again the probabilities of this exact distribution in terms of what they're setting up. And here it is. And so notice this is pretty much a relative frequency distribution. Notice how it adds up to 1. Here's your x column. Here's your probability column. Now, each of these outcomes, it's just a term, it's called a random variable. And so that's just a quantitative way of describing, what the outcomes could be. So from now on, when you read about the term random variable, that's just a description of the outcome, numerical description of the outcome. Now, in this chapter, we're dealing with what's called the discrete random variables, where that is they can have there's a finite number. It can only assume a certain clearly separated or defined value. Whereas the continuous random variable, we're going to do that in Chapter 7, and that's where we're going to be looking at infinite values in terms of ranges. Okay, and that's when we're going to go back to looking at like the bell-shaped curve. That's going to be in Chapter 7. In this chapter, this is going to resemble a lot like our relative frequency distributions. So again, a discrete random variable is, again, a random variable. It can assume only a certain or finite number. It's going to be a separated value. And usually it's a result of counting something. So it's going to be an observation. So again, this is exactly like what you would look at with a relative frequency distribution. So to calculate your expected value of your outcome, of your probability distribution, the formula would read mu is equal to the summation of, so you're going to have to take the random variable x, multiplied by the probability of x, and simply add it up. That's going to be called your expected value. And so for this one, notice you've got the number of cars sold, 0, 1 through 4. You've got the probability of each of these outcomes. So if we wanted to figure out how many cars you would expect to sell on any given day, we'd set up a column x times the probability of x, and then simply add it up. So 0 times 0.1, 1 times 0.2, 2 times 0.3, 3 times 0.3, and then 4 times 0.1, and then add it up. And then that would give you what's called your expected value. So as you can see by these calculations, once you did multiply it, here's your column where you multiply it, you added it up, you'd get an expected value of 2.1, which basically means you expect to sell about 2.1 cars on any given day or any given Saturday. Now, the next calculation we're going to get into is called the variance or the standard deviation of a discrete probability distribution, and that formula basically is right there. And to break it down for you, the mu value that we already calculated, for example, in the previous slide, that's the value we're going to be using right here. So notice we're going to have an x minus mu. We're going to have an x minus mu where we're going to have to square it. Then what we're going to have to do is take the probability of x of each of these outcomes and multiply it by x minus mu squared. And then the last step will simply be to add up that column to get our variance. Now, then once we do that, we can simply take the square root of the sigma squared, which is our variance, and that, of course, is going to give us what's called our standard deviation. So that part is really consistent from the previous chapters. And as you can see in this slide, it's walking you through all the steps. So here, notice we've got the outcome column, you got the probability of x. Here's your x minus mu, and just to remind you that mu was equal to 2.1. And so, for example, 0 minus 2.1 gives you they're showing the actual calculations, every one of these numbers where they're taking 0 minus 2.1, 1 minus 2.1. They're basically showing you what you're doing that you'd have to put in this column, okay? Now, once you do that, then you square everything in this column, and you get this column. And then you take these numbers, all right, and then you multiply these again by their individual probabilities, and that's what you get in this final column. And then finally, you simply add it up, you get 1.29. That is basically called your variance. And then once you take the square root of that down here, you get your standard deviation, okay? So this isn't a difficult thing. It's just you have to do it a few times just to get the process down. But this, again, is a new formula you need to know how to work in this chapter. Now, the basics, again, of a binomial probability distribution. This is a specific type of discrete probability distribution. Has a lot of applications in the real world. And a couple things is when we look at one, there's only going to be two possible outcomes. We're going to say success or failure. The outcomes are mutually exclusive. The results are of counting, and the trials are said to be independent. And to keep talking about some of the more characteristics again, so in terms of successes or failures, our focus is going to be on the number of successes. X is going to represent the number of successes given how many trials we have. So we always use the variable X just to kind of label it, okay? The probability for each success or failure is constant. And then again, here's your independence rule. Now, one thing I'm going to deviate a little bit from the formula in this chapter is your textbook likes to use the pi symbol to represent this probability of success. I like to use the letter P instead because I think when people see pi, they think 3.14, and that's not what they're wanting you to do. So I'm going to use the letter P. In a moment, I'll show you how that formula looks like. So notice here's your function, and to me it looks more complicated. Down here you've got the pi symbol. So what I like to say is, you've got your combination formula, which again I have it on the other slide that I'm giving you as well. This pi, I'm going to call that P1 minus P instead of this. But here's the thing. I'm going to actually have you go into the tables to do these calculations. I'm not going to require you to actually do this calculation just because of all the factorial calculations. So use the tables for this one. And again, as you can see, that it looks more complicated than what it really is, but this is just showing you your combination formula. And again, I'm not going to have you actually do any of these calculations. All this is computerized these days, but it's just a basic idea. It gives you all the different outcomes. It's called your combination counting rule. That's part of the binomial function. Now, there are a couple unique formulas to give what's called the expected or the mean or the variance. And this is where I'm going to give you a different formula. I'm going to recommend you do this one as n times p. Again, there's that pi symbol I think that confuses people. And then for the variance, just do np times 1 minus p. I think that makes it less complicated. So you can see here's one of the probability tables we're going to be using for the binomial distribution. And down here you go to the back of the textbook, it's in your appendix. Let's say you had n is equal to 6 trials. Notice for values of p, again I'm calling that p as in your probability. And so for example down here where you've got for example n is equal to 6 and let's say the probability is equal to 0.05. Notice they give you all the different listings of outcomes that x could be 0 through 6. You always could have 0 successes, but all these tables have all these binomial formulas already calculated for you. So I don't expect you to do those. What I do expect is you to be able to go to the back of these tables, locate that constant probability, and then try to calculate which of these numbers are you going to need to solve for the problem. And I got some examples I will show you a little bit later on how to do that. And so for example, let's say you had n is equal to 6 and you wanted to know that the probability that x is equal to exactly 1 or 2 or 0, whatever. So if you want x is equal to 0, you'd say it's 0.735. If you wanted x is equal to 2, you'd say 0.031. So it's really that simple. You just have to go into these tables and figure out what does x have to be and just pull the number. Now I'm not going to test you in Excel, but Excel does all these calculations that your table does as well. And if you're ever interested in learning it, you could email me. I can show you how to do it. It's not difficult, but Excel can duplicate all of these tables very easily as long as you know which function to plug in. So in your textbook, they have the section called a cumulative binomial probability. Typically what that comes up to is, let's say this is the Excel example, but you would have the same example in the back of your book in your tables. If you wanted something that was asking for at least 7, which means the probability that x is greater than or equal to 7. Again, this is Excel, but let's say you went to the back of your textbook. You simply locate it. Let's say in this case, n is equal to 12. Now, you couldn't look this exact p up because your textbook's not going to give you 0.762, but let's say you had a constant probability. You'd go back, find n is equal to 12, find the probability of the constant. It's going to give you all the successes, but the cumulative nature is if it's 7 through 12, you'd have to go to the table and find these numbers and then add up all of these probabilities. That would give you 7 through 12. So again, you'll see that on some of the illustrations I have coming up on some other slides. Now the Poisson distribution is the other distribution we're going to take a look at, and it typically is interested in the number of times or occurrences that something happens, an event happens during a specified interval of time, distance, area, or volume, and so forth. All right. And so, again, we'll use the probability tables in the back, but I think you'll find that the formula to actually get the probability of the outcome isn't too bad. You could actually do that one on your calculator. So here it is. Here's your probability function. Notice you've got mu. I'm going to write this up down here. Mu to the x, e to the negative mu, divided by x factorial. And your main focus when you look these up and do the calculations is going to be to calculate the expected value. And once you can do that, you plug it in here and you can get your probability. Notice that the idea of a mean is the same as before. It's n times pi, or again, we would say n times p. I think that's easier to remember. And this is just showing you the basic calculation. In this case, you had a random sample of 1,000 flights. You had 300 bags that were lost. Thus, the mean would be you'd expect 0.3 or 30% of the bags to be lost. That's going to be mu. It says if the number of lost bags follows Poisson with mu is equal to 0.3, find the probability of losing 0 bags. That means that x is equal to 0. So what they did was they just plugged these numbers into the formula, 0.3 to the 0, e to the negative 0.3 divided by 0 factorial, and they got this number. And again, you could also look this up in your tables in the back. And again, here's your Poisson tables, and notice you typically look it up by the mu value. So in this case, mu is 0.3. We wanted x is equal to 0. You could just go to the table. There's your answer, and that's basically all you have to do. So I would suggest you use the tables. That'll save you some time in terms of the calculations.